Hello everyone, my name is Cruz. I'm from Portugal. I recently finished my master degree in mechanical engineering, and this work, entitled Develop of a mini-tensile approach for sheet metal testing using digital image correlation, is a portion of my final master thesis. Uniaxial mechanical tests, tensile and compression, are widely used to determine the behavior and the mechanical properties of metallic materials. These tests are universally used, so are normalized by different institutions like ISO, ASTM, DIN, etc. The specimen geometry is perfectly defined by these institutions, and the sample can be considered a macro-scale specimen. However, this type of scale, the macro scale, is not the most adequate for some applications. For example, when it's necessary to evaluate the life of a particular mechanical component in service, where it is neither possible or convenient to remove a large amount of material. Another example is when it's desired to perform compression or dynamic fatigue tests of sheet metal, where a low ratio thickness length promotes the occurrence of buckling phenomena. So, the solution for these cases is to reduce the scale of the specimen from a macro to a meso, micro, or nano scale. The main objective of this work is to develop a mini-tensile device for sheet metal mechanical characterization using mesoscale specimens. To verify the utility and the accuracy of the mini-specimen results, a series of preliminary tests were performed before the device development. For that, the prototype represented on this slide was used to test specimens on a mesoscale. For mini-tensile tests, dimensions and geometries are not yet standardized, and they vary according to different authors. So, in this study, two types of geometries were produced by milling. One with a width of 2 millimeters and a uniform length of 12 millimeters, and the second with the same width but with a smaller length, 2 millimeters. The material tested was magnesium sheet with 0.6 millimeters of thickness, and during the test, the force was acquired by a load cell. Talking now about the strain measurement, traditionally on the macrotensile test, extensometers are used to measure the longitudinal and transversal strain. However, in mini-size specimens, it is difficult or is impossible to attach these standard extensometers for strain measurement. So, for mesoscale specimens, some optical methods, such as the digital image correlation, DIC, proved to be more suitable. In this work, the DIC technique was used with the following setup and specifications. In this slide, I represented the results for the preliminary tensile tests. Is also represented a reference curve corresponding to a macro-scale specimen test for the same material. It's possible to note that the curves have the same shape and can be easily compared with a macro reference. The strength parameters, namely the yield strength and the ultimate strength, are similar, but as you can see, the elongation is more sensible to miniaturization, especially the ultimate strength elongation and the total elongation. However, these results can be considered satisfactory and provides a very good evaluation of mechanical properties for this material. It is also represented on this slide two videos with the strain distribution during the time of the test. It's visible that the distribution is uniform along the gauge length, what is according to what happens normally in a macro scale geometry. After the preliminary tests, a new prototype, the mini sample tester device, was developed. This equipment, represented on the image, is capable to test mini specimens in uniaxial solicitations, compression and tension. Has a maximum load capacity of 2.5 kilonewtons and a possible stroke of analysis near to 43 millimeters. Analyzing now the equipment, the linear motion is guaranteed by a step motor connected to a ball screw. The motion is transmitted to a free body, the linear motion, and where is attached the mobile grip. The fixed grip is mechanically fastened to an S-type load cell, and all the components are guided by two rectified shafts. This layout allows to test materials in tension, but also in compression, because all the components are in a common longitudinal plane. This is the major advantage of this layout, because it reduced any kind of bending moment that can appear on the specimen. The ball screw has a step of 2 millimeters and guarantees a backlash level of 0.5 microns. This characteristic is extremely relevant in solicitations with different directions. To evaluate the behavior of the mini sample tester device, some cycle tests with tensile and compression loadings were performed. For that were tested specimens with a thickness of 1.1 millimeters and with a geometry with a gauge area of 2 times 2 millimeters, the same used in the preliminary tests. The tests began with a compression solicitation until a maximum force of minus 1.3 kilonewtons. At this point, the direction was inverted and the specimens began to be solicited in tension. When the maximum force of 1.3 kilonewtons was reached, the direction was inverted again, and this sequence was repeated one more time. From the analysis of the engineering curve represented, the material behavior in the plastic phase is visible for both in compression and tension. It is also visible that during the cycles, plastic accumulation occurs and is responsible for the curve gap. In conclusion, this work reports the development of a mini-tensile equipment, the mini sample tester device, for sheet metal mechanical characterization. This device uses the digital image correlation, DIC, as the method to evaluate the strain distribution in the specimen plane. First, some preliminary tests in the first equipment were performed to evaluate the behavior of different geometries of specimens in a mesoscale. The obtained curves have the same shape as in the case of a standard tensile test, thus showing that miniaturized specimens are a powerful technique for sheet metal mechanical characterization. The utility of the DIC technique for mesoscale tests was also confirmed. Then, having in consideration these preliminary tests, the mini sample tester device was developed with a maximum capacity of 2.5 kilonewtons. This equipment is capable to test specimens in tension, but also in compression loadings. Finally, some cycle tests were performed in the new equipment to evaluate the potentiality of the mini sample tester device. The results obtained were very satisfying because it was possible to reach plastic strain both in compression and tension. Thank you very much for your attention.